unfortunately, it has now gotten to a stage where the springs are so stretched and overused that the spring constants that we found have completely changed. And I don't even know if there's some kind of non-linearities. But now, if I was to use the apparatus and plot the curves, the displacement of this cart, it looks nothing like that predicted by the theory. So I didn't bother bringing it along, but instead, what I'm going to do is just show you some plots of the curves and a few animations using similar parameters to that of the model. So anyway, it's a little bit disappointing. I mean, you might think, oh, just replace the springs. It's easy. Just get 100 springs and we'll be set for all the lectures. Well, that's true actually, but it's something I've just not gotten around to do. So anyway, we're looking at forced oscillations today. So this is an application of the second order linear differential equations that we've been looking at. Now I'll just draw your attention to some of these dot points at the start of this section. I guess that summarize what I'm hoping you can take away from this lecture. It's not so much the methods, it's just some of the concepts that I hope you can take away from the lecture today. So firstly, it says this first dot point is how to determine the steady state solution of a forced oscillator. So I'll be talking about steady state solutions. And also, along with that discussion, I'll talk about what are known as transient solutions. So I'm hoping you can take away from the lecture an understanding of transient solutions versus steady state solutions. I'll also be talking about resonance of such systems, and also with a system with damping, it's often referred to as practical resonance. So we'll analyze this using the differential equations and the solutions, and actually we'll see how, well, we'll investigate some of the phenomena associated with these systems, and in particular have a close look at how you can get beats arising in the displacement curves. So I'll explain all about that as we progress. So this is the differential equation, well, this one actually. This is the differential equation, this non-homogeneous linear second order ODE, where the coefficients m, c, and k are all positive constants throughout. So I guess the sort of system we're going to be considering is where we have a mass on a spring that's oscillating. We'll take displacement to be measured from the equilibrium position, and the positive displacement I'll take directed downwards. It doesn't really matter which way we choose, which direction we choose. But just when I was deriving these equations and working with all these equations, I was always using the downward direction to be positive displacement. And now what's more, we're introducing a driving force. So this whole system, so we're attaching this system up here, like the end of the spring, we're attaching to some kind of mechanical oscillator. And we'll only focus on the case where, where this force due to that mechanical oscillator is a cosine wave. All right, so just quickly, you may have seen this if you've done the Math 1052 course, but Newton's second law is what we're using to model this system. So the mass times the acceleration, so the second derivative of the displacement, is just the net force being applied to that body, which we can interpret as the sum of all the external forces acting on that body. So in this case, the model that we're considering is the sum of the forces, including a spring restoring force. And this is actually Hooke's law, using Hooke's law, so where the restoring force is proportional to the displacement. So if I pull the spring back this way, there's a restoring force going in the opposite direction. Okay, so proportional to displacement, plus a damping force. Oh, and by the way, relating to that, the restoring force from the spring, that's the spring constant we'll denote by K here. So that actually gives rise, the spring restoring force gives rise to this term in the equation, that Ky. Okay, so K is just the constant of proportionality that depends on the spring. So different springs, different spring constants. Okay, in our model, we'll assume a linear damping force. So that is linear, it's in the sense that the force due to damping is proportional to the velocity, all right, just the velocity, so it's not a nonlinear term. So only really talking about small velocities here, so it's a reasonable approximation to the damping force. So in other words, as the object oscillates, as it moves, it experiences a resistive force in the opposite direction to motion. All right, this is known as damping. Okay, so, I mean, for example, you can imagine some different quantities may contribute to a damping force. For example, the cross-sectional area might have something to do with it, the cross-sectional area of the object, that is. The medium through which it's travelling. If it's travelling in air, water, or honey, you can imagine this will all give rise to a different kind of damping force. And finally, we're assuming an external driving force, and that's due to the mechanical oscillator that we're attaching to the system. All right, so it's this external driving force that we'll assume depends on time. Okay, and what's more, we'll assume it's of the form of this cos function. All right. So this is the ODE that we're interested in solving, in analysing. We know that the solution, the general solution, I keep writing this down, don't I? YH plus YP. The general solution comprises two parts, right? The YH, the homogeneous solution, is the general solution to the corresponding homogeneous equation, and the YP, the particular solution, is the only thing that contributes to this non-zero right-hand side. All right, so we've certainly seen how to determine the homogeneous solution. All right, M, C, and K are all constants, so we should be able to just write down the characteristic equation, which becomes m lambda squared plus c lambda plus k equals 0, and work out values for lambda to write down the YH. Okay, but what we can do is also work out the particular solution. Now we've got a few options here, or a few different situations to consider. And in particular, it depends on the driving frequency of this mechanical oscillator. So in other words, it depends on that this factor omega, okay, that appears on the right-hand side. What we can do, I mean, especially in this this apparatus I was talking about, that for which this provides a model. In that apparatus, we attach the whole system to the mechanical oscillator, and we can change the input frequency. We can change the driving frequency simply by turning a dial, right? So throughout this whole analysis, what you could do is think of this omega, even though it's a parameter in the model, it's a parameter in our model, think of omega as being something that we really can tweak, right? We really can change however we see however we want to. All right, so anyway, to solve this, to write down the particular solution, we can use the method of undetermined coefficients that I talked about last week. All right, we look at the right-hand side and see it's a cosine. So the method of undetermined coefficients then tells us that we can just make an appropriate guess for the particular solution, that it's also, it's going to be some linear combination of cos and sine functions, all right, in this way. Okay, so one thing we can do is, just making that guess, that educated guess based on the method of undetermined coefficients, substitute that into the left-hand side of the equation and then match up coefficients. All right, now I'm not going to do that in the lecture, but certainly one thing you could verify for yourselves is that the values of the constants A and B are given by these two expressions, equations 7 and 8 at the bottom of the screen there. All right, and one thing in particular is we introduce this quantity, the omega naught, as the square root of k on m, which we actually call the natural frequency of the system. Okay, so that's the method of undetermined coefficients. There's one thing to observe, is that in the case that omega and omega naught coincide, all right, so this omega naught is actually what we end up with for the homogeneous solution. So in particular, if we take the case that omega is omega naught and the case without damping, I should have included that in the text, so where there's no damping, so where C equals 0, that's the damping coefficient. So I mentioned the damping force is proportional to velocity. As you can see from the equation, it's this term here that is proportional to the velocity. Okay, so in this case, when omega equals omega naught, we have the homogeneous solution just being an arbitrary linear combination of cos omega naught and sine omega naught. Okay, so in that case, you can see if C was 0 as well, so without the damping, this would be the homogeneous solution. And then if omega is omega naught, you can see that this guess for the particular solution would not be suitable, all right, because these terms occur in the homogeneous solution. And then we'd have to apply that modification rule in the method where we just multiply through by t in that case for our guess to the particular solution. All right, so you can still get complications arising like that, but nevertheless, I'll just point out, so we compare, so just compare those two expressions that we'd need to modify our guess in that case. All right, so what we're going to do is just look at two different cases where the system is undamped, so not a particularly realistic model, but we can still investigate some of the properties of the solution, some phenomena that arises in that case, and then we'll look at the more complicated, though realistic, damped case. All right, so over the page, we'll start just looking at the undamped solutions, the undamped oscillations. I'll just make that make the other one a bit bigger. And I'll just keep up this equation. So this is the equation of motion that we're dealing with in this case. All right, so now without damping, so the undamped case, so that's the case that corresponds to C equals 0. Just for the moment, what we'll do is assume that the driving frequency omega is not equal to the natural frequency of the system, omega naught. So when I'm talking about the natural frequency of the system, as you remember on the previous page, we defined omega naught in terms of the spring constant K and the mass of the object attached to the spring. Okay, so omega naught is defined to be the square root of K on M, and this is what we're calling the natural frequency of the system. So if you think about in terms of what we have control over in the system, imagine once we set this thing in motion, imagine we can't change the mass and we can't change the spring constants. Okay, but what we can change is the frequency of the driving force. So just keep that in the back of your mind. I mean, I know I've already mentioned that, but just think about that as we progress through through the lecture. So for the moment, we'll assume that omega squared is not equal to omega naught squared. So just have a look at, in that case, when C equals 0, you can see these two coefficients which come out of that method of undetermined coefficient calculation. When C is 0, B will be 0. All right, so that's the coefficient of the sine term. And the only non-zero coefficient will be A. And we'll further assume that omega squared is not equal to omega naught squared. So you can see why we do that, because complications are going to arise in that case. All right, and what's more, we also know that in that case, we'd have to modify our guess for the particular solution. All right, so just looking at those expressions for A and B on the previous page, you can see we get for the particular solution just this cosine term. And it turns out we can actually write the general solution. So I've mentioned the homogeneous solution right at the bottom of the previous page. This is the homogeneous solution, plus the particular solution gives the general solution, right? But what I've actually got here is the general solution just written as the sum or the superposition of two cos functions. So it's actually this term here that is the homogeneous solution, YH. So let's just have a quick look at why we can write the homogeneous solution like that. So there's a trig identity that's useful in this case. So the cosine of the difference of two quantities, so say cos of A minus B, this is the trig identity, is just cos A cos B plus sine A sine B. All right, so in the case where just looking at this expression that I've got written down here, looking at that expression, well, using that trig identity, what about cos omega naught t minus delta? Applying that trig identity, we just end up with cos omega naught t times cos of delta plus sine of omega naught t sine of delta. And now if I multiply through by that c, okay, what we can do is compare that with the YH that I had from the previous page, which was just A cos omega naught t plus B sine omega naught t, right? So we still have these two arbitrary constants in this form of the YH, but in this case they're presented as C and delta. All right, so what we can do then is match up these terms. So set our arbitrary coefficient A, just rewrite it in terms of C and delta as C cos delta, and B we match up with C sine delta. Okay, actually in this way, what we find is we can work out what the amplitude of these oscillations are, right? So in this case, C would just be the amplitude of those oscillations. All right, and delta is just some kind of phase shift in the oscillations. All right, so in this case now, for the general solution, we've just got a superposition or a sum of these two cosine functions. And as it says in the text, these represent a superposition of these two harmonic oscillations with two different frequencies. Right? One is the natural frequency of the system. So in the sense, it's something that we can't change if we can't change the springs or the mass that's oscillating. And the other is the input or driving frequency given in terms of omega. All right, so we could try looking at the maximum amplitude of the particular solution, right? Because in some sense that, well, you can see actually that depends on omega. So as omega changes, in fact, as omega naught squared minus omega squared becomes really small, the amplitude of this oscillation, right, coming from the particular solution gets bigger and bigger, right? And in fact, you can see in the limit as omega naught squared minus omega squared goes to 0, that actually blows up to infinity. All right, so that's what's discussed just down here. And this phenomenon of the excitation of large oscillations is, well, by matching input and natural frequencies, is known as resonance. So resonance is when the driving frequency coincides with the natural frequency of the system. I mean, if anyone plays a musical instrument, I know there are resonant frequencies there. I mean, you can think if you play, I don't know, a clarinet, for example, this clarinet has a natural frequency, and when you blow into it, the reed at the mouthpiece oscillates, right? And this is the driving frequency. Although it turns out that with the clarinet, you can push buttons and change the natural frequency of the system, right, and create different notes. But it's a bit of a thin analogy, right? Because three-dimensional sound waves and these one-dimensional oscillations we're talking about here are a little bit different. But yet, there are still some similarities in the phenomenon. All right, resonance is one. I mean, I know when you tune a guitar and you sort of pluck two strings and you want them to sound the same, and you turn the pegs, you can sort of hear these as you get close to the note on the string that you're changing. You can actually start to hear beats until it the two notes coincide, and then you can hear some kind of resonance. Anyway, so that's the definition of resonance. So, by the way, what happens if we do have resonance? Then what we can do, so I guess I can just put a little box around this discussion here. In the case of resonance, what can we do to determine the particular solution? Well, in this case of resonance, where the driving frequency coincides with the natural frequency of the system, we would have to modify the guess, right? Because we know that cos omega naught t occurs in the homogeneous solution, right? And it turns out after modifying the guess according to the method of undetermined coefficients, so we multiply the original guess just by t, and we end up with the particular solution being given by this. So it's a sine wave, but you can see the amplitude of those oscillations are growing linearly in time, right? Think of the amplitude as growing linearly in time. So the amplitude grows as t increases. And so as t gets bigger and bigger, there's nothing that's going to stop the amplitude from getting bigger. So this is in the case of resonance here. Okay, but what about when we're really close to resonance? So that is when omega naught squared minus omega squared is small, but not 0. Okay, well it turns out it turns out that beats arise. And I'll show you what I mean by that in a minute. But first, let's just see, well, exactly, more analytically, I guess, what we mean by beats. So let's just take this solution that corresponds to some initial conditions given by y of 0 is 0 and y dashed of 0 is 0. So this is just imposing those conditions on the general solution we had before. We end up with, with this difference of cosine functions. All right, now using that trig identity I had before, what was it? Cos of a minus b equals cos a cos b plus sine a sine b. And now actually if I rewrite this identity, but this time replace b with negative b, so I write cos of a plus b. So since cos is an even function, so cos of negative b is still cos b, so that doesn't change. But sine is an odd function, so sine of negative b is negative sine. So all we end up doing is changing that to a minus. So we subtract sine a, sine b. And now if I take the difference, of those two cosine terms, so I'll just add in a minus sign here and a plus sign there. So that implies that cos of a minus b minus cos of a plus b. You can see the product of cosine functions cancel, and the product of the two sine functions doubles up, so that equals 2 sine a sine b. All right, and actually, if you set a equal to omega naught plus omega on 2t, and b equal to omega naught minus omega on 2t, you end up recovering this identification here, right, using this trig identity. All right, so we've got a difference of these cosine terms here, which is exactly what we've got in this manipulated trig identity that I've used, and I'm just replacing that with 2 times the sine of these guys, or the product of the sines of these two expressions. So that's exactly what that is. So now consider this. In the case that omega naught minus omega is small, right, in the case that's small, in fact, let me rewrite this. I just want to... I always mean to rewrite the order of these expressions. So imagine if omega naught minus omega was small. So look, all I'm doing here is just rewriting the order of the signs. It's nothing. It's just for convenience. So for this sine function, the frequency is very small. So in other words, the oscillations are infrequent, so not occurring as much. So the frequency is small compared to the frequency of this guy. So the way you can view this is that we've got a sine wave whose amplitude itself is oscillating or expanding and contracting, right, according to this sine function. All right, so I've got a couple of plots actually of just some different values for a particular example. Let me just zoom out a little bit so we can get this all on one screen. All right, so this is that solution to the initial value problem that I stated before. So it's just this function rewritten with a couple of values in for omega naught and omega. So here, I don't know if you can read my writing. I've zoomed out a bit far, but this is omega naught is 2 pi, omega is pi, f naught here is 10, and m is 1. So those are the values that I've used in this formula. Okay, and that's what the oscillations look like for that particular case. But as we change the driving frequency, and as it gets a bit closer to that natural frequency of the system, so in this case, omega naught is still 2 pi, but now the driving frequency omega I take to be 1.8 pi, so we're getting reasonably close, and close enough to see the phenomenon of beats that I'm talking about. All right, so namely, now we can see the frequency of these oscillations, so that's describing how the amplitude of these oscillations, the sine of omega naught plus omega, are changing with respect to time. So they're growing and contracting and so on. And so this is what we call beats, right? When we're close to resonance, so the driving frequency is very close to the natural frequency of the system. We're close to resonance. Beats arise. Actually, these two diagrams I've turned into a little animation. So it's exactly with those quantities. So here, the W naught is just 2 pi. All right, the W on the screen there is just the driving frequency. So this is where the driving frequency is 0. And this is just a plot as we increase the driving frequency. And so what we can see as we watch this little animation progress is how the dynamics changes according to, as the driving frequency changes. So actually, just let me pause it for a second, point out that each frame of the film that I've got here of the animation is a plot of the dynamics, right? So this is a graph of displacement versus time. So as we're watching the animation, we're not observing any dynamics as such. Each frame of the animation is just a plot of the motion. So it's corresponding to, there's the value of pi, and that was one of the diagrams I had up. So what we're seeing is just how the behavior changes as the driving frequency gets closer and closer to the natural frequency. Once it gets up above 5, I think it's around that point that you can start to see the beats emerging. You might be able, you can probably start to see them about now. And so I'll just pause it there. And so for a value of 5.4, close enough to 2 pi, you can definitely see the phenomenon of beats in that case. And of course, I took this as far as I could go. Now, once it gets really close to the natural frequency, I had to change the vertical scale of the system because these oscillations really started getting big. And just watch that vertical scale just get bigger and bigger. So, I mean, there you can see, I had to stop just short of omega naught. The MATLAB didn't like dividing by 0, so I had to just stop one frame short of omega equals omega naught. But I'll also just point out that this little calculation we've done here, where the particular solution works out to have oscillations growing linearly with time, you can see here as we're pretty much at resonance, that plot there, although it's still a product of sine functions, you can see that pretty much looks like it's growing linearly with respect to time. So, I mean, even though it's not exactly at resonance, it's still very close, we can observe that phenomenon. And there are very large oscillations. Okay, so just back to the workbook now. I guess we can ask the question, well, what about in the case of damping? So that was all for the undamped case, right? So that was I guess, slightly unrealistic model where there's no damping involved. Okay, but if we include damping, we actually end up, well, and so this is always in the under-damped case, right? We end up with exponentially decaying oscillations. So here, this quantity, the Greek symbol psi, is just the square root of k on m minus c squared on 4m squared in terms of those parameters I used before. All right, so the key difference here is we now have these, we now have this exponential term in the homogeneous solution. And this is only in the case of underdamping, right? I mean, if it was an overdamped system where the damping was very high, I mean, you can imagine this if we put our spring in a jar of honey or something and, say, pull it down and release it with some initial condition. I mean, it's conceivable. You can imagine that the object would not have decaying oscillations, but it might just slowly retract back to equilibrium and not oscillate. Okay, so this maybe in honey might be a nice example of an overdamped system, but I'm only going to be considering underdamping in this case. All right, well, because of this exponential term, and remember C and M are positive numbers, so that means we've got this these exponentially decaying oscillations. So what that means is as t gets larger, these oscillations become smaller and smaller due to the presence of this exponential term. In fact, we can see that the YH in this case, the homogeneous part of the general solution, goes to 0 as t increases. So in fact, as it says in the text here, the general solution in this case, in the case where there's damping, and in the underdamped case, will actually approach the particular solution as t goes to infinity. So now this is where I can introduce these concepts of a transient solution and a steady state solution. So what we say is that this general solution, and in fact even the solution that corresponds to some initial conditions, we can say this is a transient solution. So transient meaning temporary, or it goes away after a period of time. That the solution of this form, because YH goes to 0 as t goes to infinity, this is referred to as a transient solution. We actually use this type of language a lot in analysis of differential equations and solutions of differential equations, transient solutions and steady state solutions, not just in this context. All right, so that's called a transient solution in the sense that it's temporary, it goes away after a period of time, and it approaches a steady state solution. And that steady state solution is always going to be given by the particular solution, right? Always in this case, because the exponential term goes to 0 as t goes to infinity, we always just end up recovering the particular solution in that large time limit. This is known as the steady state solution. All right, and usually all physical models have some kind of damping. That is, models of this sort, they always have some kind of damping involved. So this is really what happens. This is a much better model of the system. So one other thing we can see is that the amplitude is actually finite. The amplitude of the oscillations is finite, even as the driving frequency becomes close to the natural frequency of the system. I guess here I should be talking about psi, not omega naught. Okay, I should be talking about psi. But there may be some large maximum of the amplitude at some specific value of the driving frequency. All right, and in fact, we can see this if we have a look at that particular solution. So we investigate the steady state solution, have a look at the particular solution. We've seen how to manipulate this sum of cosine and sine functions into just a single cosine function using those trig identities. All right, so we've already seen how to progress from one line to the other with these coefficients A and B given on one of the previous pages, so given back here. Right, so now we have damping, so C is not equal to 0 in this case. All right, so remember what I was saying earlier is that imagine we have some control over that driving frequency. Indeed, in the apparatus I was talking about at the beginning of the lecture, that was the one thing that I had control over. I could turn a dial and change the driving frequency of the system. Okay, and we find that the amplitude of the oscillations, so the amplitude of the steady state oscillations, so that's this C star, ends up being expressible in terms of those quantities, omega and omega naught and F naught and M and C and so on, expressible in this way. Right? So if omega is something we have control over, that's the driving frequency, then you can see that C, this amplitude of the steady state oscillations, the C star, has some dependency on omega. So we can ask the question, well, how does it change with respect to omega, and does it ever reach some local maximum? Well, we can investigate that by differentiating this function with respect to omega. I won't do that explicitly, but the result that comes out of that is that we require this equation to hold by setting this derivative to be 0, and it turns out that can give rise to a local maximum. In other words, when omega squared is equal to this expression in terms of all the other parameters in the model, including the natural frequency of the system. All right, now if C squared is large, or if the damping C is large enough, right, in particular if C squared is greater than 2m squared omega naught squared, this will be negative, and it turns out it won't have any real solutions. So in that case, the amplitude of those steady state oscillations just decreases and has no local max. So it just decreases as the driving frequency increases. However, if the damping is small enough, so if C squared is less than or equal to 2mk, then we can actually find a solution to this equation. In fact, the driving frequency, we'll call it omega max, so the driving frequency in that case, we just take the square root and is written in this form. Okay? Remember, we only need to take the positive square root because the driving frequency we assume is a positive number. So corresponding to that frequency I'm calling omega max, and that is the frequency that gives rise to a local maximum of the amplitude of the oscillations. The corresponding amplitude is then given by this expression, just by substituting in that omega max value into here. And this is what we call practical resonance. So whereas we saw in the case where there was no damping, we saw at resonance, the oscillations just blew up to infinity, right? However, in this case, we don't have that. We have in some cases, if the damping is small enough, we can obtain a maximum value of those oscillations. Okay, so just a couple more demonstrations of this on the laptop. So I've got, where is it, this practical resonance. I'll just open this up. Come on. So I'll just open this up and show you an example. It actually corresponds to, just while we're waiting for it to open up. It corresponds to this system here. No, it doesn't want to open. It corresponds to this system here, so this differential equation. And for this example, now it comes. Okay, for this example, we work out that that omega max, the driving frequency that gives rise to the maximum amplitude, is just 1 on root 2. All right, it's quite an artificial example, and the corresponding maximum amplitude is about 11.5. So in this diagram here, I've got the solution curve that will change as we change the driving frequency, and that horizontal line across there is about 11.5. So that's at the maximum amplitude. Okay. By the way, this is what we're plotting. That's the solution. That's what the solution looks like, leaving omega as a variable. All right. So now I won't. I'll just play this really quickly. I'll just zoom through it. So as we increase the driving frequency, you can see what's happening as it gets larger and larger and closer to that value. What's 1 on root 2? It's about 0.7, a bit larger than 0.7, right? As we get to 0.7, it hits that maximum amplitude, and beyond that starts decreasing. Now here you can actually observe probably up to about t equals 5 here, you can observe the transient solution. So you can see the solution curve there looks a little bit different to the rest of it. Everything beyond here is the steady state solution. Right? And I guess one thing to observe, just going right back to the beginning, notice it looks like the steady state solution is just a horizontal line. Well, that's at omega equals 0. You can see when omega equals 0, cos of 0 is 1, so the right-hand side is just 10, and certainly the particular solution in that case would just be yp equals 10, right? So that's all that's detecting in that example. So this was just a little artificial example to demonstrate practical resonance. However, one thing I decided to do, because I couldn't bring the apparatus in, I actually made a plot, or made a little animation of what the solution curves look like as we were using the cart on the track and producing plots that way. So we actually found that at resonance, we ended up with, at practical resonance, I should say, we ended up with a graph looking something like this. And curiously enough, when we were very, very close to resonance, we ended up with these transient beats. Okay, so we ended up with these beats. Remember how, in our analysis, how those beats arose, or how they arose, I should say. We had a difference of cosine functions and rewrote that as a product of sine functions. Well, in this case, we've got an exponentially decaying homogeneous solution here. We've still got our particular solution out here, and here we've got some transient beats. So just as I'm finishing up, this is a rendition of the behaviour of that particular system. I mean, with all the quantities, all the parameters that we actually measured and used for the model, this is what it looks like. So this, remember, each frame of this movie is a plot of distance in meters versus time. Okay, and each experiment we were doing, we were letting it run for a little over 2 minutes. So I made sure in these plots I used pretty much the same scale. I think it worked out to be about 5.15 was the driving frequency that gave that maximum amplitude. So you can see, I'll just stop it there because now it just the amplitude just decreases. But you can see very close to that practical resonance at about omega is 5.15, you actually have these transient beats either side of either side of that maximum. All right. Anyway, guys, I'll stop there and see you next time.